Okay, so continuing with section 2.8. So now we are going to talk about basis for a subspace. Now in the previous video I showed you that there are two special subspaces related to a matrix A of size m by m. So an m by n matrix A, but one is called the column space of A and the other is called the null space of A, or null. So we'll denote them by call A, null A. So call A is the subspace which is generated by the columns of the matrix, or which means all the vectors which can be written as a linear combination of the columns of A are going to be in this subspace. Null A contains all the solutions of the homogeneous equation Ax is equal to 0. Now we talk about a basis for a subspace. A basis for a subspace H of Rn is a linearly independent set in H that spans H. So remember, any space that you see in this, here we are talking about subspace, but later on in chapter 4 we will talk about vector spaces. So these are generated by fewer vectors than they have. For example, the R2, there are infinitely many vectors in there, but they are basically generated by only these two vectors, 1 0 0 1. So this forms a basis for R2. Just these two vectors, they form a basis for R2. So and why? Because any vector you think of in R2 can be written as a linear combination of these two vectors, and this is called the standard basis. We are going to talk about it right here, down here. But so example 1, if A is an n by n invertible matrix, then columns of A are linearly independent and span Rn by IMT. Okay. Now if A is an n by n invertible matrix, then columns of A are linearly independent because it's invertible. So there will be n pivots. So it means n columns are linearly independent, and it means it will span Rn. So that's why column of A form a basis for Rn. Now if it is not an n by n matrix, if it's an m by n matrix, then columns of A can never span the Rn. Okay, the columns of the identity matrix In forms a basis for Rn. That's what basically I showed you here, because the identity matrix for space 2 will be this. So that is the first column here, and this is the second column here. So they form a basis for the space. Now the columns of the identity matrix are denoted by, so E1, we have names for them, E1, E2, E3. So here this is E1, this is E2. In R3 space we have three basis vectors. In R4 space we will have 4 basis vectors, and so on. So if we have n, so this will be En, n basis vectors. So this type of set we call it the standard basis for Rn. But now we can have non-standard basis for our subspaces, and we will see how we can find them. We are going to find these bases for the subspaces that we just described in the lecture in 2.8, the column call A and for null A. So matrix A and its echelon form are given. So if the echelon form is not given and you are asked to find a basis for call A or null A, so your first job is to convert the A matrix into echelon form, at least echelon form. If you want to go ahead and do the reduced echelon form, it's your choice, but basically in echelon form is kind of a must. So you have it in echelon form here, and now for the column A, what we will do, so by the way, the basis for column A is easy to find, less work, as you can see here. The null space requires more work. So what we are looking for is how many columns have a pivot in them. So if you look at this matrix in the echelon form, we have a base pivot here, and then we have the pivot here. So we have the pivot in the first and the third column. So it means the first and the third column are linearly independent. We cannot have the other two, because if we combine the other two with these, or even if one of them with these two, then the set is no more linearly independent. So just column 1 and column 3. And how you pick them? You look for the pivots. The columns which have pivots in them, that's what is going to form the basis. And also note here that A is of size 3 by 4. Okay, A is of size 3 by 4. So columns are of size 3 by 1. Okay, each column is size 3 by 1. So the column, the basis, the vector in column space will be of order 3 by 1. So what do you do? So basis for, this is a basis, I should say, because there can be other bases as well. So a basis for column A is -3 to -3. And what are these? These are just the columns of A I'm picking. Now we could also pick these, the columns of the echelon form. Those are also basis for form a basis for the column space of A. Or maybe I should write it, or 1 0 0, 6 4 2. Sorry, 6 4 0. Yep. And even from here, this could be reduced to, instead of 6 4 0, because we can factor out a 2, so this could be replaced by 3 2 0. So see, there are many bases that we can write, at least more than one way you can give the basis. But if you, in the book, I think there is written just the columns of A, so you may just give it your answer like that. So for the column space, you only look for the pivot columns. Okay, those are going to give you the basis for the column space. So what about the null of A? For that, you have to actually write down the solution, the X vector, or the whatever you call it. So all the variables. So here we have because there are 4 columns, so there are 4 variables. So X1, X2, X3, X4. So looking at the echelon form, we can notice that X2 and X4 are free variables. Why? Because they are not, in that column we do not have a pivot. So what are free variables, or columns with free variables? Are the columns in which there is no pivot. So now we have to, we should be able to write now the rest of the vectors in terms of those free variables. So the other variables should be able to, so other variables would be X1 and X3. So we should be able to write X1 as a linear combination of X2 and X4, and also X3 as a linear combination of X2 and X4. So we try that. We see from the second equation of the echelon form that we can say 4x3 plus 5x4 equal to 0. And from here I get x3 is equal to minus 5 over 4x4. So remember, what are your free variables? You are not going to write, I mean, of course you can get from here, you can get x4 equals negative 4 over 5x3, but this is not what we want. We want to write in terms of the free variable. So x3 is not a free variable, x4 is a free variable. So I should write x3 in terms of x4, not x4 in terms of x3. Okay, so this is not. Okay, so here we are, we got that. Nice and easy. But now we have to do a little work with the x1 because of all the numbers in that row. Now, if you want to reduce this work that I'm going to do over here, if you want to reduce this, then you have to go one step further, at least by making this quantity 0 using the pivot 4 as the pivot. So if you want to do one more row operation, you may, but it's your choice, but I'm just going to go with the equations. So the first row, I can write the equation x1 minus 3x2 plus 6x3 plus 9x4 is equal to 0. Okay, why am I saying 0, by the way? And here also I said 0. Well, because for the null space, what do you do? Null space, remember, is the solutions of all the of the equation ax is equal to 0. So how do you find the solutions? What do? You have the A matrix, and you augment the 0 matrix, right? The 0 vector, the 0, 0, 0. Okay, I will just call it O. So you augment that 0 vector here, and then you apply the row operations to get A in the echelon form. So, but what will happen with the 0, this column? The zeros will just remain 0 no matter what row operation you apply. So this the given echelon form of the matrix, we can use it to imagine that on the right side of the equation will be the 0. So we can write the equations by assuming the right side is going to be 0, because we are trying to find the solutions of ax is equal to 0. So that's how I am getting 0 here and the 0 over here. So now x1 will be equal to 3x2 minus 6x3 minus 9x4. But x3 is in terms of x4, so I substituted that for x3. Doing the math around here or algebra, we end up getting this thing, which brings us here. So x1 is equal to 3x2 minus 3 over 2x4. Now we write our final answers, that what are the solutions going to look like. So this will be x equals, so x1, but x1 is, maybe if you want, you can write one more step here as one more thing in here. So we can say x, which is equal to x1, x2, x3, and x4. That's how our vector x is. But x1 is now 3x2 minus 3 over 2x4. x2 is just x2 because it's a free variable. x3 is minus 5 over 4x4. That's what we found. And then x4 is x4. But now we can split it like this. I have shown you this before. This is the parametric form. So what does it show? It is showing that all the vectors that can be written as a linear combination of these two vectors, those are going to be in null A. So these are the type of vector which, when multiplied with matrix A, are going to give you the 0 vector. So these two now we will say form the basis of null A. So therefore basis of or for null A is, so you'll put parentheses, big parentheses, and then you will put the vectors in. And notice now these are 4 by 1 vectors. The size of these vectors is 4 by 1. Now if in the answer I saw they are using decimal, well, only convert a fraction into a decimal if it is whole, like it comes to an end, it stops. If it goes on and on, approximated value, don't write that. Give always the exact value. So sorry, this will be minus 1.50, this will be negative 1.25 and 1. Close the bracket and close the braces. So this is the basis. That's how you find the basis for the null A. So that's it in section 2.8. Now we will move to hopefully chapter 4.